Welcome to Astronomy Daily. I'm Anna.
And I'm Avery. It's Monday, March 9th, and if you've been following the news this past week, the universe has been spectacularly busy.
We've got alien signals going missing in the cosmic static, astronaut brains getting physically rearranged in space, a dramatic launchpad rescue story straight out of a thriller, and a genuinely mind-bending discovery about why Earth's seasons work the way they do.
Plus, we're asking one of astrobiology's most provocative questions. Did life on Earth actually start on Mars? It's a packed episode. Let's get into it.
Here's a thought that's going to sit with you for a while. What if we're not alone in the universe, but we've been tuning to the wrong frequency this whole time?
That's essentially what a new study from SETI is suggesting. Researchers Vishal Gajjar and Grace Brown have published work showing that stellar space weather, the kind of turbulent plasma and solar activity that stars constantly churn out, could physically distort alien radio signals before they even leave their home solar system.
So here's how SETI searches typically work. For decades, scientists have been scanning the sky for very tightly focused narrowband radio signals, extremely specific frequencies that nothing natural in the universe should produce. If you detect one of those, the thinking goes, it's almost certainly artificial. It's almost certainly someone.
And that logic is still sound, but the new research highlights a gap in the reasoning. Even if an alien civilization sends a perfectly clean narrowband signal, their own star's environment might smear it out before it escapes. Plasma density fluctuations and stellar winds or a burst from a coronal mass ejection can spread that tight signal across a much wider range of frequencies, reducing its strength at any single point below what our detectors can pick up.
The team ran simulations of the million closest sun-like and red dwarf stars and found that 70% of stars would broaden a signal by more than 1 hertz, 30% by more than 10 hertz, and if a coronal mass ejection happened to fire off at the moment of transmission, the broadening could exceed 1,000 hertz, making the signal essentially invisible to the way we currently search.
And red dwarf stars are the biggest culprits here, and that's particularly significant because red dwarfs make up about 3/4 of all the stars in the Milky Way. A lot of our SETI attention has focused on those systems precisely because they're so common. And it turns out they may also be the most likely to garble any messages being sent from their planets.
The good news is that identifying the problem is the first step to solving it. The team says this gives us a framework for redesigning searches to remain sensitive even when signals are broadened, to look for what actually arrives at Earth, rather than what was originally transmitted.
It's a bit like realizing you've been trying to tune into a radio station, but the signal had passed through a foggy atmosphere on its way to you. It's not that the station isn't broadcasting, it's that we need a better aerial.
And that's a much more hopeful framing than nobody's out there. The universe might be full of voices we just haven't learned to hear yet.
Now, if you're planning a trip to space or if you're just a big Artemis fan, this next story is worth paying attention to, though we want to say upfront that it's fascinating rather than alarming.
A new study published in the Proceedings of the National Academy of Sciences has found that spaceflight doesn't just change your perspective on life, it literally shifts the physical position of your brain inside your skull.
A team led by Rachel Seidler at the University of Florida analyzed MRI scans from 26 astronauts taken before and after missions to the ISS, missions ranging from a few weeks to over a year. To measure the brain's actual movement, they aligned each person's skull across the 2 scans so they could track the brain's position relative to the bone itself.
And what they found was striking. The brain shifts upward and backward inside the skull. It also physically deforms, stretching and compressing in different directions. The sensory and motor regions show the largest shifts. And crucially, the longer someone spent in space, the more pronounced these changes were.
The underlying cause is what you'd expect from microgravity. On Earth, gravity constantly pulls fluids, including the cerebral spinal fluid surrounding your brain, downward. In space, that force disappears. Fluid redistributes toward the head, the brain effectively floats in the skull, and it responds to different forces from surrounding tissues.
Previous research already knew the brain shifts upward in space. What makes this study important is the level of detail. Instead of treating the brain as one object, the team divided it into more than 100 regions and tracked each individually. That revealed patterns, like opposing lateral shifts on each side of the brain that had been canceling each other out and going unnoticed in whole brain averages.
The reassuring news, most of the changes recover within 6 months of returning to Earth, and the astronauts themselves didn't report symptoms like headaches or cognitive fog. The researchers stressed that this doesn't mean people shouldn't go to space, but as missions get longer and as Artemis starts taking humans back to the moon and eventually towards Mars, understanding these effects will be important for designing proper countermeasures.
It's a reminder that space is a genuinely alien environment for the human body. We evolved under one gravity, and every time we leave it, we're running an experiment on ourselves. The more we understand those experiments, the safer we can make long-duration spaceflight.
Now, for a story that is, in the best possible way, a bit of a thriller. In November last year, something went wrong at the historic Baikonur Cosmodrome in Kazakhstan, and nobody was entirely sure it could be fixed in time.
It started on November 27, 2025. A Soyuz rocket lifted off from Launch Site 31 carrying the Soyuz MS-28 spacecraft with 2 Roscosmos cosmonauts and NASA astronaut Christopher Williams aboard. The launch was successful. The crew docked with the ISS without incident.
But post-launch inspection footage revealed significant damage to the pad itself. A component called the service cabin, which retracts into a protective cavity to shield it from engine exhaust during ascent, hadn't been properly secured. The powerful rocket exhaust dislodged it, and the structure fell several meters into the launch trench, deforming bridges, access walkways, and other critical infrastructure.
The space community was skeptical this could be fixed quickly. These are heavy, complex structures, but Roscosmos committed to the repair, and it turns out their long history with the Soyuz system gave them an unexpected advantage. Spare service cabins had been sitting in storage, left over from refurbishment plans dating back to the 1970s.
The restoration effort was enormous. Over 150 personnel worked on the project. They completed over 250 meters of welding, painted nearly 2,400 square meters of structures, replaced all fastening units, and fully updated the electrical systems. The replacement cabin, originally built for an older Soyuz variant, needed modifications to work with modern hardware.
And in under 2 months from the initial damage assessment, far faster than most observers anticipated, Roscosmos announced the pad was fully restored and declared ready for operations.
That means Progress MS-33, an uncrewed cargo ship, is now cleared to launch from Site 31 on March 22nd. It will deliver around 2.5 tons of supplies to the ISS: propellant, water, food, scientific equipment, and crew parcels.
It's a genuinely impressive piece of engineering under pressure, and it's a good reminder that behind every rocket launch is an enormous amount of groundwork. Literally, in this case, that never makes headlines until something goes sideways.
Okay, pop quiz. Why do we have seasons?
Earth's axial tilt. We all learned this in school. When the northern hemisphere is tilted toward the sun, it's summer up here. When it's tilted away, it's winter.
Exactly right. And most people also know that Earth's orbit around the sun is slightly elliptical. We're a bit closer to the sun in January and a bit farther away in July. But we're usually told that effect is minor, and it doesn't significantly change our seasons. Well, a new study published in Nature suggests we may have been underselling that distance effect quite significantly.
The research led by John Chiang at UC Berkeley focuses on a specific feature of the Pacific Ocean called the cold tongue, a strip of cooler water that stretches westward from South America along the equator. This cold tongue is closely tied to El Niño and La Niña cycles, which influence rainfall, drought, and weather patterns across huge swaths of the planet.
What Chang and his colleagues found is that the changing Earth-Sun distance creates its own separate annual cycle in the cold tongue, distinct from the tilt-driven one. And the two cycles are slightly out of sync. The distance-based one runs about 25 minutes longer than the tilt-based one. That doesn't sound like much, but it means that over about 11,000 years, the two effects drift from being perfectly in phase to perfectly out of phase.
When they're in phase, like they are roughly today, The effects reinforce each other. When they're out of phase, as they were around 6,000 years ago, they partially cancel, producing a much weaker seasonal cycle in the cold tongue. And since the cold tongue drives El Niño, that means El Niño patterns themselves would have been dramatically different in the deep past.
The mechanism works in a counterintuitive direction too. While axial tilt creates north-south temperature differences, the distance effect creates an east-west contrast between the continental hemisphere of the Americas, Africa, and Eurasia, and the ocean-dominated Pacific side. That contrast drives trade winds, which in turn shape the cold tongue.
It's worth noting the study is entirely model-based. It's a prediction that will need observational verification, but it opens fascinating questions for paleoclimate science. If Earth's orbital shape was changing the cold tongue over 22,000-year cycles, some ancient climate records may need reinterpretation.
And there's something wonderfully humbling about it. We've been telling school children for generations exactly why seasons happen. And it turns out the full picture involves a subtle cosmic clockwork we hadn't fully accounted for.
And now for our final story today, and honestly, one of the most mind-bending things you can contemplate on a Monday. What if you're not from Earth?
In a very literal biological sense, possibly.
A new study is revisiting the concept of panspermia, the idea that life doesn't necessarily originate independently on each planet, but can travel between worlds. And the vehicle? Asteroid impacts.
Here's the premise. We know that when a large asteroid or comet slams into a planet with enough force, it can blast material into space, rocks, dust, and potentially anything living inside those rocks. We've actually found meteorites on Earth that originated on Mars, blasted off by ancient impacts. So the physical pathway definitely exists.
The question has always been, could anything survive that journey? You're talking about the ejection itself, an enormous shockwave, then exposure to the vacuum and radiation of space for potentially millions of years, then a fiery atmospheric entry and high-speed impact at the destination.
The new research suggests the answer might be yes, under the right conditions. Some microbes, particularly those that form hardy spores or live deep within rocks, could potentially survive all of those stages. The rock itself provides shielding from radiation during transit, and the numbers game matters. Even if only a tiny fraction of ejected material survives, the sheer volume of material blasted around the early solar system means some viable biology could have made the crossing.
The Mars connection is particularly intriguing. Early Mars was, by many accounts, a better candidate for life to emerge first than early Earth. It cooled faster, it had liquid water earlier, and it had a gentler gravitational well, making it easier for material to escape. If life arose on Mars billions of years ago and hitched a ride on an impact-ejected rock, Earth could effectively have been seeded.
Which would mean that if we ever find microbial life on Mars or evidence of ancient life there, we'd face a fascinating interpretive challenge. Did life arise independently on both worlds, or are we all, in some deep ancestral sense, Martians?
The study emphasizes this is still highly speculative. Panspermia remains a hypothesis rather than established science. But as our ability to study Martian samples improves, especially with future sample return missions, we may eventually be in a position to test it directly.
Either way, the question is deeply fascinating, and it gives a whole new flavor to the phrase, out of this world.
That's Astronomy Daily for Monday, March 9th. From scrambled alien signals to astronaut brains, from a launchpad resurrection to the hidden clockwork of Earth's seasons, and the possibility that we're all secretly from Mars.
It's been a great episode. If you're enjoying the show, please leave us a review wherever you listen. It genuinely helps new listeners find us. And share an episode with a friend who's curious about the universe.
You can find us at astronomydaily.io, and we're at Astro Daily Pod on X, Instagram, TikTok, YouTube, and Tumblr.
We'll be back tomorrow with more of the universe's greatest hits. Until then, keep looking up.
Bye for now.